All right. Well, welcome back to the ZAG seminar. Today we're happy to have Fumiaki Suzuki, who will tell us about acyclic varieties of even index.
All right. So thank you for the introduction, and I'd like to thank the organizers for the invitation. I'm very glad to give a talk here at ZAG seminar. And today I'm going to talk about my recent joint work with John Cruz and Autumn. So let me first start with the introduction. So here is the setting that we work today. Let X be a smooth projective variety over the complex numbers, and let be a smooth projective curve. And let's assume we have a fibration X over a curve B. And in this setting, the natural question would be whether it admits a section or not. And of course, it is not always the case, but we can still ask under which condition it does. And then in this direction, there is a nice geometric result.
Sorry, I don't think your slideshow is showing on the. I mean, we can only see your front slide, I think. Yeah, maybe if you go to full screen or something.
Yeah, so okay, so maybe I can just so now the situation changed.
Yeah, we see a different slide, I think, but yeah, is it possible to see the like a full screen or something?
Screen. Okay, so let me try again.
Yeah, there you go.
So now it's different. Now it's
actually not showing a full screen, so that's.
But you can still see it, right? I think.
Yeah, we can see the.
I see. I'm using that full screen now, so probably something went wrong. I don't know. Let's see.
We're still on the sort of first slide.
Yeah, that's true.
Okay. Right. Yeah. Try again.
Okay. Sorry. Let me try again. So in the illustration, there is a nice geometric result due to Graeber Harry star, and then they show that there always exists a section if the generic fiber is rationally connected. And this result generalizes a classical theorem of 10, saying that the function field of a complex curve B is a C1 field.
I'm sorry, we can't see the Graeber star theorem.
Oh, really?
Yeah.
Okay, so can I just maybe try to share in a different way because.
Okay.
So maybe just share my desktop instead. Can you see?
Yeah, much better. This is perfect, I think.
Much better.
Yeah.
Much better. Okay, great. Great to hear that. Okay, so and this result of Graeber Harry star is related to a certain classical question of Serre. Okay, so he asks the following question: does a fibration over a complex curve admit a section if the generic fiber is always acyclic? So here, all acyclic means that all higher cohomology group of the structure sheaf are 0. And Serre came up with this question after he observed that any all acyclic variety of a finite field admits a rational point. And then he asked, how about over other C1 fields? And indeed, this question has a positive answer. The result of Graeber Harry star gave a positive answer to a special case of this question. However, in general, this question has a negative answer, as proved by Graeber Harry Mesa star. And actually they show that, there exists aggregate surface vibration over a curve without section. Okay. And later, Lifon and Starr gave more explicit constructions of such aggregate surface vibration. Okay. But one can still ask whether a certain weaker statement would be true. So here is another question. So does a vibration have an index 1 if the generic fiber is always cyclic? So here, the index is the greatest common divisor of the degree of a multisection of this vibration. So this question essentially asks whether it admits multisections of coprime degrees as in the spectrum under this setting. Right? And it is important for us that there is no local obstruction to this question. So in other words, any vibration over curve B with generic fiber or acyclic, there is no multiple fiber. In fact, this is an easy consequence of Riemann-Roch formula. And one can rephrase this by saying that the local index is equal to 1 everywhere over the base curve B. Okay. But nevertheless, several mathematicians expected the answer to this question would be negative. So in Eno and Collet-Telen-Voisin expected like that. And in particular, Collet-Telen-Voisin asked whether one can construct a cyclic surface vibration with the index not equal to 1. And the main purpose of this talk is to show that such a vibration indeed exists, and thereby to give the first counterexample to this index question. Okay, so here is our main theorem. So we show that there exists an aggregate surface vibration over P1 of even index. So in other words, any multi-sections of this vibration has even degree over the base curve P1. So here are some remarks to this theorem. So first of all, one can actually find such a vibration, such an aggregate surface vibration over P1 defined over the rational numbers. And in fact, the rational numbers would be the minimum possible field over which one can construct a counterexample to the index question, because this question has a positive answer over FP bar if we further assume the Tate conjecture and one technical assumption that the second batch number in the total space is equal to its narrow Severi rank. But however, this construction of the rational numbers is a bit involved. So today we will focus on the construction of the complex numbers. Okay. So any questions so far? All right. So now, before moving on to the construction of our example, let me first explain the applications of the main theorem. So there are 3 applications, and the first of them will be on a certain question in number theory. So let's start with the aggregate surface vibration of the main theorem, and let Y be its generic fiber. Then Y is an aggregate surface over the function field of the base curve P1, and we call the field F. This Y has a remarkable property, namely the index of y is not equal to 1. So y does not admit 0 cycles of degree 1, while it does over any completion at close point of the base curve P1, because the local index is equal to 1 everywhere locally, as I pointed out previously. In other words, the Hasse principle fails for 0 cycles of degree 1 on y. So they exist everywhere locally, however, not globally. Okay, so here is a question of polyethylene. So can the failure of the Hasse principle on y be accounted for by the reciprocity obstruction? So here the reciprocity obstruction is an obstruction to the existence of 0 cycles of degree 1 on y. And it is defined in terms of H1 net homology with torsion coefficient. And the answer for this question is no. One can show this directly using our explicit construction. But in fact, this is a more general phenomenon. Here's the theorem of Wittenberg. He showed that any smooth projective or cyclic variety over the function field of a complex curve B, there is no reciprocity obstruction. So it'd be interesting that even then, there is an OS cyclic variety without any 0 cycles of degree 1, as shown in our main theorem. Okay. So the second application is on the integral Hodge conjecture. So let me first explain what it is. So for a smooth projective variety X over the complex numbers, we have 2 subgroups of the cohomology, integral cohomology of even degree. First one is the subgroup of algebraic cycles, which is defined as the image of cyclic class map from child group of X to the integral cohomology group of even degree. And another subgroup is a subgroup of integral Hodge classes, which is by definition the pullback of the middle piece of Hodge decomposition by the natural map from the integral cohomology to complex cohomology. Okay, and it is known that first is contained in the second. Integral Hodge conjecture predicts that they are actually equal. And this conjecture holds for several cases. For instance, when p equals 0 and dimension x, this statement holds for trivial reason. And it is also true for p equal 1, which is known as Lefschetz 1-1 theorem. However, in all other cases, in general, the statement is known to fail. The first counterexample was constructed by Attia and Hirzberg. And later, Kolar gave another type of counterexample. And since then, there have been found many other counterexamples to the integral Hodge conjecture. Okay. So why is this integral Hodge conjecture related to the index question? So that is by this theorem of Polyethylene and Poisson. So they show that if we have a fibration over curve with generic fiber or cyclic, then the push forward by the natural map gives a surjection on H2 homology. So in other words, the index question always has a positive answer for homology classes. And in this setting, the homology classes automatically Hodge. So as a result, there exists a certain integral Hodge class, which maps to the generator of the H2 homology of the base curve B. Okay. So as an immediate corollary, we get that the integral Hodge conjecture fails on the total space X of the Enrique surface vibration of the main theorem. But not only that, we can actually say a little bit more. In fact, it fails modulo torsion classes, even modulo torsion classes. And this is simply because in the quotient, this beta gives a non-zero element. Okay, so this class beta is not algebraic, but we can show 4 times beta is algebraic on our example. The reason is that the index of our example divides 4. Okay, and from now on, I want to talk about the third application, but it is in fact built upon this failure of the integral Hodge conjecture modulo torsion classes. So, it is the third application is on the Abbe-Jacobi map. So usual Abbe-Jacobi map is defined on cycles homologous to 0, and its target is the Griffith intermediate Jacobian, so given by the Hodge structure of integral cohomology group of odd degree. And in general, this complex torus is transcendental. However, if we restrict this map to the subgroup of cycles algebraically equivalent to 0, then its image, which we sometimes call algebraic intermediate Jacobian, is an abelian variety. And moreover, this induced map psi p, which we also call the Abbe-Jacobi, is regular. So more precisely, for any smooth projective variety S with the fixed point S naught, and for any convention P correspondence on the product, the composition of the push forward by gamma and psi p gives a morphism of algebraic varieties from S to the algebraic intermediate Jacobi. So in other words, this psi p defines a certain invariant on algebraic cycles with values in an abelian variety, which behaves well with respect to algebraic families of cycles. And generally, homomorphism from algebraically trivial cycles to an abelian variety with analogous property is called regular. Here is a classical question of Moore. Is Abbe-Jacobi map psi p universal among all regular homomorphisms? So in other words, if we have a regular homomorphism phi, then does it factor through psi p? Several positive answers to this question are known. So for instance, in codimension 1 and codimension equal to dimensional x, the answer is yes by the theory of Picard variety and Arvanez variety. And surprisingly, the answer is also yes for codimension 2, as proved by Moore using the Mercury Excision theorem. Okay. So in particular, this question has a positive answer up to dimension 3. But on the other hand, Walker made some important observation that this Abbe-Jacobi map factored through another regular homomorphism. So here we have the Abbe-Jacobi map. It factored through psi p sub w. It's a surjective regular homomorphism, and its target is the intermediate Jacobian given by the Konjuba filtration. Here, the Konjuba filtration is generated by classes, cohomology classes supported on a proper Zariski closed subset of codimension p minus 1. And you can think of this as odd degree analog of the subgroup of algebraic cycles. And this pi p is a natural isogeny of abelian varieties induced by the inclusion of Konuba iteration into integral cohomology of degree. Okay, so as a result, if this psi p is universal, then it forces the kernel of the isogeny to be trivial. And in fact, one can describe this kernel explicitly. And this vanishing of the kernel is equivalent to say that the sublattice given by the Konuba iteration inside the lattice of integral cohomology is saturated. And it turns out this last condition on lattices is too strong to be true in general. So here's a theorem. So let X be a smooth projective variety such that two condition holds. So first, we assume that the integral Hodge conjecture fails in degree 4 modulo torsion classes. Okay. And the second condition is that Chow group of 0 cycles on X is supported on the surface. So in other words, there is a Zariski closed subset of dimension 2, so that the inclusion map, the pushed forward by the inclusion map, gives a surjection on Chow 0 groups. Okay, so under these assumptions, the conclusion is the following. So there exists an elliptic curve E such that the sublattice given by the Konuba iteration inside integral cohomology is not saturated for pico 3 on the product of X and E. And as a consequence, the Abe-Jacobi map is not universal in convention 3 on the product. Okay. And here, elliptic curve is important in the key step of the proof of this theorem, where we construct a certain non-zero torsion class, non-zero torsion cycle in the kernel of pi 3. And the non-zero torsion cycle eventually gives non-zero elements in the kernel of the isogeny pi 3. Okay, and what is important for us is that the theorem can be applied to the X of the main theorem. We have already mentioned that the first condition on the failure of the integral Hodge conjectures, conjecture in degree 4 modular torsion classes. And as for the second condition, one can in fact show that char 0 of X is equal to Z. So in particular, it is supported on a point. Okay, so as a result, we get a certain fold on which the Abe-Jacobi map is not universal in codimension 3, and obtain the first counterexample to the Murray's question. And moreover, by taking the product with the projective space, one can also construct a counterexample in higher dimensions and also in all other possible degrees. So this settles Murray's question completely. Okay. Okay. So so these are the applications of this main theorem. So from now on, I want to talk about the construction of the Enriquez surface vibration in the main theorem. Okay. So we are going to construct the Enriquez surface vibration over P1, but before that, we have to construct the Enriquez surfaces themselves. And for that, we consider a certain projective bundle, actually P1 bundle, over P2 plus P2, given by O of 2, 0 and O of 0, 2, given by the direct sum of O of 2, 0 and O of 0, 2. And inside of the ambient space, we take a complete section of 3 tautological divisors, and that's going to be our S. So by dimension counting, this S is a surface. But if S is general, then one can actually show S is an Enriquez surface. And from now on, I want to give a proof of this by describing its K3 ethyl double copper. Okay, so first, I want to summarize the notation that I'm going to use in the following. So P of A is going to be the ambient space of the surface S. And here we have the components, and these components give a natural sections, which we call E1 and E2. P of B is going to be another projective bundle over P2 close P2, given by a direct sum of O1, 0 and O0, 1. And again, the components give natural sections over P2 close P2, and we call them F1 and F2. And finally, our P5 is a projective space of the global section of O1, 0, direct sum of O0, 1. And again, components give two disjoint planes, P1 and P2 in the P5. Okay, so here is diagram about them. So first, there is a 2-to-1 map from PB to PA, given by taking squares relatively over P2 close P2. And this is ramified along F1 and F2 and branched over E1 and E2. And on the other hand, map on the left is the blow-up of P5 along two disjoint planes, P1 and P2. And exceptional divisors are exactly F1 and F2. Okay, so now we restrict this diagram over S, then its double cover is inside PB as a complete section of twice of tautological divisors. And its image in P5 is a complete section of 3 quadrats. And the point is that since S is general, this complete section in P5 has empty intersection, does not intersect with either of these disjoint planes. So it follows that map on the left is an isomorphism, and map on the right is ethyl double cover. And to conclude, it's enough to observe that complete section of 3 quadrats in P5 is a K3 surface. Okay, and now we want to construct Enriquez surface fibration fibered into Enriquez surfaces in PA. And for that, we take the product of P1 and PA, and inside of that, we take a complete section of 3-to-1 divisors, and that's going to be our X. And here, of 2, 1 is the pullback of O2 on P1 tensor pullback of O1 on PA. And we are going to use a similar convention in the following. Okay, so by construction, if X is general, then the first projection gives an Enriquez surface fibration. And moreover, it has the following basic properties. So for instance, its Kodara dimension is equal to 1. X is simply connected, and in fact, its integral cohomology groups are all torsion-free. And Hodge diamond looks like this. So what is important here is we have zeros on the edges. So this shows that the total space X itself is in fact all acyclic. In this illustration, the block conjecture predicts that child 0 of X is equal to Z, and it is indeed a case here. And I want to show this fourth statement of the lemma in the following. Okay, so we start with the complete intersection curve C inside X. So that is the complete intersection of 2 ample divisors. And here is a picture. So here we have a fibration from X over P1. And here we have complete section curve C, and by the choice of C, it intersects with every fiber of this vibration. Okay. And now I want to claim that any zero cycle on X is supported on this curve C modulo rational equivalence. So now let's take an arbitrarily zero cycle on the total space X. Then maybe some points supported on singular fibers, but since the total space X is smooth, so we can apply the moving lemma so that we can assume that they are supported on smooth fibers. Okay, so now I want to apply this theorem of block case and Lieberman, saying that char zero of any Enrique surface is equal to C. So this allows us to move our zero cycles along smooth fibers, and now we can conclude that char zero of X is indeed supported on this curve C. Okay. And from here, by applying decomposition of the diagonal technique, one can conclude that degree zero part of char zero of X is in fact isomorphic to the Albanese variety of X. But on the other hand, Albanese has dimension equal to H1 of structure sheaf, OX, which is zero since X is OS cyclic. So this concludes the lemma. Okay. All right. And to prepare for the proof of the main theorem, we need to study the geometry of X. So we have actually a similar diagram to that of Enrique's surface. And here we have X, a complete section of 2 1 divisors inside P1 close PA. Its double cover is inside P1 close PB, and that is a complete section of 3 2 2 divisors. And its minimum model is inside P1 close P5, and it is the complete section of 3 2 2 divisors. But the main difference here is that this complete section has no empty intersection with the blow-up locus. The blow-up locus consists of 2 components, and this complete section intersects with each of the components along 24 points. So in total, we have 48 points, which we call Qi, comma j. And now map on the left is the blow up along this 40 points Qi, comma j, with exceptional divisors Fi, comma j. Okay, and then map on the right is a 2 to 1 map. It's a double cover ramified exactly along Fi, comma j. Okay, and let's call the image of Fi, comma j on X Ei, comma j. Okay, so as a result, we have 2 sets of 24 planes on X. But in the proof of main theorem, we will focus on one of them. So the 24 planes, E1, comma 1 to E1, comma 24 will be important in the proof. Okay. So here is our main theorem. If X is very general, then any multisection of this first projection has even degree over the base curve P1. So in other words, the index of X over P1 is even, which is what we wanted to show. All right. So here is strategy in the proof. So in the proof, we are going to show a certain key congruence, which holds for any multisection M and any 12 tuple of integers between 1 and 24, and which looks as follows. So on the one hand, we have degree of the multisection M over P1, and on the other hand, we have the intersection product of M and the corresponding 12 planes. And this congruence is modulo 2, right? So first, let me explain why this congruence implies our main theorem. So the whole point is that left-hand side of this congruence, degree of the multisection, doesn't depend on the choice of the 12 tuple. So this implies that the intersection product of M and each of the 24 planes is constant modulo 2. So again, by using this congruence, one can conclude degree of the multisection is even because 12 is even. Right? Okay, so in the rest of the talk, we will focus on showing this key congruence. Okay, so here's a strategy for the proof of the congruence. So we combine monodromy and specialization arguments. So in step 1, we use monodromy arguments to reduce the congruence for any 12 tuple to the congruence of a single 12 tuple. And in step 2, we will show the congruence using a specialization argument. And in fact, we will use specializations twice. Okay. And from now, I want to explain this proof, each step in detail. So let's start with step 1. And we start with the universal family of the threefold X. And then there is a natural action of fundamental group of the base space U on the set of 24 planes on fibers by permutations. Key lemma is that corresponding monodromy representation is surjective. And for the proof of this lemma, we use Lefschetz pencils. Okay, and this key lemma finishes the reduction step. Indeed, let's assume the congruence for a single 12 tuple. Then the point is that left-hand side of the congruence, degree of the multisection over P1 is monodromy invariant. So while the right-hand side is not. So basically, we can keep applying the monodromy actions until we get congruence for all 12 tuples of integers between 1 and 24. Okay. Okay, so now it remains to show the congruence for a single 12 tuple. And for that, we specialize X to another Enriquez surface vibration Y. And Y is going to be a complete section of 3 1-1 divisors inside P1 cross PA. So the same ambient space as that of X. Again, if Y is general, then the first projection gives us Enriquez surface vibration over P1. And this Y has pretty similar properties to those of X. And the only difference is that the Hodge number is a little bit smaller. And geometry of Y is also pretty similar to that of X. But the only difference here is that this complete section of 3 1 2 divisors inside P1 close P5 intersect with the blow-up locus along 2 sets of 12 points, so which results in 2 sets of 12 planes on Y. Okay, and again, we will focus on only one of them. And so the 12 planes E1, 1 prime to E1, 12 prime will be important. Okay, so here is our first specialization. So we specialize X, which is a complete section of 3 2 1 divisors, to Y, which is a complete section of 3 1 1 divisors. But we also have residual components, excuse me, But all of the residual components are supported on fibers. Here's a picture of the specialization. So the 24 planes on X specialize together with X. And after specialization, they are distributed as 12 planes on Y and 4 planes on each of the residual components. So in other words, this chosen specialization gives a certain partition of 24 planes into 12 planes on Y and 3 sets of 4 planes. So in particular, this determines certain tuple of integers between 1 and 24, such that the corresponding 12 planes on X specialize to the 12 planes on Y. Right? So here is again a picture of the specialization. And let's recall that we wanted to show certain congruence between the degree of multisection and the intersection number of M in the 12 planes. But by the specialization, by using the specialization homomorphism, now it's enough to show a similar congruence on Y. And here, what is important is that if we choose the specialization general enough, then this whole union is simple normal crossing. And moreover, these 12 planes on Y are disjoint from singular locus of the union. Okay, and to show this congruence on Y, we will use the second specialization. So here, okay, so second specialization. So we do not describe the specialization explicitly here, but the idea is that we specialize Y to a union of 2 components, such that the fiber class minus 12 planes is double as a Cartier divisor on each component. Okay. So here is a picture of the specialization. So Y naught is one of the components, and it dominates P1. And it has 12 planes on it. And one can actually directly show that on this Y naught, fiber class minus 12 planes is double. This Y naught prime is the other component. And in fact, this is supported on fiber. And also, this Y naught prime is disjoint from all 12 planes. So in fact, this divisor is just a trivial on Y naught prime. Okay. But I want to give just final comment here that this divisor is not double on the union of Y naught and Y naught prime. So whole point is that the intersection of 2 components is an Enrique surface, and the difference of 2 divisor is in fact 2 torsion line bundle on the Enrique surface. And this also shows that why this method doesn't work for homology classes. Okay. But in any case, so this shows our congruence on Y, so hence on X, and that implies that finishes the proof of the main theorem. Okay. So it's a bit early, but I want to finish here. So thank you for the attention.
Great. Great talk. Yeah, thanks. Are there any questions? Do you have any new thoughts on whether it's 2 times the class that's algebraic or it's 4 times?
Yeah, still, it's hard to exclude the index equal to, I mean, the possibility of index equal to 2. So I mean, maybe, I mean, expectation is index, it should be equal to 4, but it's not clear how to exclude that, that possibility. Yeah, so probably we should work more, we should study more on maybe it's double cover or its minimal model inside P1 close P5. It's because it seems to it seems easier to study the model, I think, but it's not clear so far.
Any other questions?
Could I ask a somewhat random and probably naive question? So at the very beginning, you said this question about the existence of sections was motivated by this, well, originally motivated by this question about the existence of a rational point. So this is a different category, but like, so in a topological setting, is there any, like, I don't know, anything interesting you can say about like when sections exist when a bunch of Betty numbers vanish like this?
Sorry, I cannot.
I was asking about the existence of like say sections in like a topological setting, like when a lot of Betty numbers vanish. Is there anything sort of analogous to what you've discussed?
I see. So right. So I think one open question is that. So I think whether there exists counterexample to the stairs question, which is simply connected, right? So I think, right. So of course, we also assume that all cyclic condition on. So yeah. So what it asks is whether there exists a simply connected or acyclic variety of a function field of complex curve, which without rational point. And I think it is open problem. So, right. So I mean, we already assume the vanishing of the cohomology groups, but we can also assume the vanishing of that portion of the cohomology. But under that condition, it is not known whether there is a counterexample to that.
Thank you.
Yeah, still have more time for questions. Okay, well, if not, then yeah, thanks a lot again for the talk. I'll just stop the recording.